My talk goes back to stellar astronomy. In a way, following up on what Theresa Lüftinger told you yesterday, I sort of go through gaps and holes and cracks that are left over overall in yesterday's and today's presentation. I sort of pick out something that I think is important, namely connecting stellar properties that you wouldn't think play any role, connect them to habitability in a very direct way, like, environments out here. How does that connect? Why is there anything that matters for habitability? And you go back to the star and observe magnetic fields, for example. I want to discuss a bit habitability, habitable zone. I'm not going into any detail. My talk is actually quite short. So habitability, what is that? What are we discussing here? It's all about having environments on a planet that make beasts like this possible, and that also provide food for these beasts. So, habitability. This is a portrait of the solar system taken quite a while ago by the Voyager probes. It's real images. Which of these planets is habitable? So I shouldn't show. I was anticipating you wouldn't guess it, but anyway, that's what we. Questions are guaranteed, and sometimes you don't know what the answers really are. You knew it, so you're not on this slide. Habitable zones. We have to, as you know, most of you probably have heard about this, we need to check where a planet actually resides around the star. We have heard some of this yesterday anyway. There are planets that are bad for becoming habitable. There are some further out that really don't make it because they are too cool. But there's more to it. It's not just the distance from the star. There's more to it. We actually need a surface, especially if we discuss about water. Now these habitable zones, especially this habitable zone that I'm going to discuss, is related to the existence of liquid water on a planet. Because that's what we think presently is the easiest way to form life. We need water, especially all life forms we have in the solar system, on Earth, of course. All life forms require water. They were formed with water or in water, and they still require water. Every single living creature on Earth needs that. So we look for liquid water, not water vapor, not water ice. That's not very helpful. We need a solid surface to get there. And we need an atmosphere. That's often forgotten. You cannot put liquid water on the moon. Doesn't work. We need pressure. So we need both. Now, how do we actually calculate what the temperature will be on a planet that has a solid surface, it has liquid water, and it has an atmosphere? There's some easy approach to this, but it's becoming complicated if you go to details. Well, first of all, let's just take a planet like, just a sphere. Forget about atmospheres at the moment. In equilibrium, the sun shines on the planet, and the planet irradiates again in the infrared, depending on how warm it is at the surface. So what's coming in gets out in equilibrium. Now, the incoming light from the sun, that's the green arrows here, hits a cross-section of the planet. And that's the energy that really is absorbed by the planet. That's the cross-section of the planet. That's the solar constant, if you will, the energy flux. And then 1 minus A. A is the albedo. That's the amount of reflected light by clouds, for example, that goes back to space. So 1 minus A is actually the energy that is absorbed by the planet. Now, after the irradiation of the planet by solar light, you lose energy again by radiation back to space in the infrared. Again, taking a solid surface like a sphere. Now, this is a sphere. The whole surface of the sphere radiates. And there if you have a temperature, we do a black body approximation. If you have a temperature on the surface, heated by the incoming light, the radiation away from that sphere is the surface of the sphere 4 pi r squared, and then sigma t to the 4th power. It has to be the same in equilibrium. coming in, getting out. And if you solve this equation, you can actually solve for Tf, the fourth power of the effective temperature. This is the incoming, the solar constant, if you will, and albedo. So you can calculate things very easily. And if you do that, you get 255 K for the Earth at 1 AU. That's not much. That's not what we have. We are used to think like something like 15 degrees centigrade, but not 255 K. That would not be the present day Earth, but we know that we have an atmosphere, so we need to take the atmosphere into account as well. Now it gets a bit more complicated. We have heard and we know there are greenhouse gases that help, CO2. There's actually also water vapor, which also helps. Methane helps, but it's not much on present day Earth. What happens is essentially there is energy coming in, this solar flux, gets absorbed at the surface, gets irradiated back in the form of infrared radiation, but then there is absorption in the atmosphere. Some molecules take that infrared, absorb it, and re-emit it again. And part of it goes back to the surface. So you see there's actually there's more energy again coming back to the surface and tries to heat it further. This is the greenhouse effect. Now you have to go through all the molecular calculations. It depends on the composition of the atmosphere, but anyway, if you do it for the Earth, we actually win 33 degrees of temperature, and that brings us to 288 K. 15 degrees centigrade, that's it. So we're done. We've explained it more or less. Does that make a habitable planet? Well, it doesn't. And that's the rest of my talk is actually to show you how much else can go wrong. This is just the beginning, this is the basics. Let me stay with the basics. I want to just go through a few things that have been developed, especially by Jim Casting and colleagues. This is from a paper in 1993. Where are these limitations in the solar system? Where can you keep liquid water based on such calculations, and more delicate calculations, of course, really taking atmospheric composition into account and so on. There are different ways of estimating in which range of radii in the solar system you can have a planet with an atmosphere about like the Earth atmosphere and liquid water on the surface. One is if you bring water vapor, if you warm up the Earth, you bring water vapor into the higher atmosphere, especially if it makes it into the stratosphere, you begin to dissociate water into H and O, oxygen and hydrogen. Now hydrogen is a very light atom, and if it's warm enough it actually escapes into space, and that happens even today, but not in big masses, but it can escape. And that's basically water destruction, what we're discussing here. So this is no good. This destroys the habitable environment on a planet. The calculations say that you have to be outside 0.95 astronomical units to prevent that from happening. Another calculation essentially says, well, actually, if you evaporate the oceans slowly, the water itself, the water vapor itself contributes to the greenhouse and heats it up more and more, and you get into a runaway greenhouse so that it heats up enormously, and that's of course also not what we want. That calculation says you have to be outside 0.84 astronomical units. There's some tests you can make. We know that Venus about 1 billion years ago also was dry. It was already in a situation about like today. Geology tells us a little bit about this. So there is evidence that about a giga-year ago, you have to make some corrections about the sun's luminosity, but that's easy. You have to be outside 0.75 astronomical units to get it right. So this is the limit. We have to be outside Venus orbit. Venus failed. How far out can you get, and can you go to keep the planet habitable? You add carbon dioxide as much as you want. You improve the greenhouse that way. Now, that's an illusion. You can actually do this. This diagram shows it. This is again from Casting. You just add more carbon dioxide from 1 bar to 10 bars to 100 bars. What on this axis basically says how much sunlight do you need. You need less and less to keep the surface warm at above 0 degrees centigrade. You need less and less if you increase the pressure of carbon dioxide out to about 10 bars. But if you increase it further, there is more Rayleigh scattering, there's actually at some point cloud formation. Then it gets worse again. So take Mars, add CO2. There's a limit. You cannot just heat it up as you want. There's a limit. And if you do that limit, you get to a result that says about 1.67 AU, and you should not be further out than that. And then again, you can take Mars. Mars as it was. We know that there was liquid water on Mars flowing, geology tells us, about 3.8 billion years ago. So at that point, it was probably habitable. Maybe it still is, actually. That provides a limit. There's a correction in here because the sun was faint at that time, fainter than now. If you correct for all of it, you have to be inside 1.77 astronomical units. And that is what defines these nice plots that you see all over the place. This is Sun, these are the planets of the solar system. You have to be in this region here. Actually, this was at the beginning of the solar system. Meanwhile, Mars is also included in the habitable zone. You have to be in here. Then you have the possibility to have liquid water on the surface if you have an atmosphere, a good enough atmosphere. There have been revisions. I don't want to go into detail. These are more recent calculations. You again see these bands. And by the way, what also was shown here, for less massive stars, they're less luminous. The habitable zone comes closer to the star. For more massive, it goes away. New calculations, this is now not distance but effective stellar flux, makes a little correction, I don't worry about this now. The Sun, Venus is outside the habitable zone starts somewhere between red and yellow. This is really difficult area to say exactly because this modeling is very tricky. Here's Earth. Mars is inside the habitable zone, but then it somehow stops. Okay. Good. This is a concept of habitable zones for liquid water. Now, does that mean once you have a planet inside this zone that you probably have a habitable planet? You expect liquid water? So the rest of my talk is to show you how delicate this actually is. Oh, this is too far. Okay. It works nicely for Earth, as we know. We have been on a habitable planet for billions of years, and it does not work so well for Venus, as I already tried to explain. What's going on here? Well, we need to look at what the Sun really is. And we heard about this from Teresa yesterday. There's radiation, there are coronal mass ejections, there's shielding by magnetic fields around the Earth, there's a wind. There are magnetospheric interactions, particles, and so on and so forth. They may all endanger habitability on a planet. So let's look a little bit closer into this. This is the solar wind, the fast winds, slow winds, and so on. I don't want to mention any of these details. Just be reminded this happens all the time. And stars probably have the same thing going on as well. Let's look a little bit into the physics of winds and what they do to a star. Winds come with magnetic fields. This is very schematic. Magnetic fields may bend back a little bit. There's a region where the magnetic fields say where the mass has to flow. It's sort of rigidly rotating here. And at some point, the magnetic fields become weak enough so that the matter says where it wants to flow and drags the magnetic fields with it. This is the Alfvén surface, as it's called. It's not so regular, and it's not exactly a line or a surface where this happens. It's a transition. It depends on the energy density, kinetic energy density, and magnetic field energy density. So first, this mass parcel is flowing in the wind from the surface out to this Alfvén radius, and then it is released and loses contact to the Sun. Now, if you take the angular momentum flow at the solar surface with this mass element here, then you get a momentum flow that is m dot omega, that's rotation rate, times r star squared. This is the stellar radius. That's just angular momentum. If you wait and you transport this out in this sort of rigidly rotating magnetic field to the alpine surface, you have the same expression again. Out there you have J is equal m dot omega, but now you have to take the alpine radius squared. And that may be a big difference. The alpine surface may be at about 10 solar radii outside. And if you take the squares of this, you see that there is a lot of angular momentum that is partial as 1 has gained from the Sun. And that means, once this is released and goes away, the Sun has lost the corresponding angular momentum. That means the Sun spins down because it has a magnetic wind. Good, now let's develop a model with this. There are many problems in solar wind and coronal physics that we don't really understand in full, but we'll develop a more phenomenological model. For example, we don't really understand how a wind is heated and accelerated. We don't know how it cools, and I'll show you why we don't know. There's also scaling between the wind parameters, temperature and density, maybe with magnetic field and the rate of rotation. And we don't know these connections. We can just observe and do phenomenology. The model that I'm going to present has actually been developed to quite an extent by Colin Johnstone. I'm not sure if he's here. You saw him yesterday. So, what we know, or we think we know, the wind somehow is driven by thermal pressure gradients close to the star. You heat somehow. You heat the corona, for example. You heat the wind. There's a pressure gradient that drives the wind away. There's more physics to it, but I don't want to go in more detail. We also know that the wind, as it expands, is not cooling adiabatically. It would just cool down and flow away. That's not what happens. These are Voyager, and back to Voyager now, measurements from 0 to about 45 astronomical units. That's across the solar system. You see the temperature coming down and then flattening and sort of going up even. That's not what you expect from an adiabatic flow. So there's heating. We don't exactly know how this works. There's additional heating. So what one does, because we don't want to put in all the physics, the microphysics and whatever it is, we don't really understand. We fit such laws here by taking a polytropic equation of state. This is pressure. This is density to the power of alpha. Alpha has to be found out from the observations, and there's a constant. This also means temperature is proportional to density to the power of alpha minus 1. What is alpha? Let's see. Well, we fit these observations that we had. We saw from Voyager and other space probes. If alpha were 5/3, this wind would behave like an adiabatically cooling wind. But it doesn't. If you take observations very close to the Sun, you find that alpha is about 1. The wind is isothermal, approximately. As you go more farther away, like in the range of 10 to 20 solar radii, you change and you increase not to an adiabatic value, but 1.5. So we have to take this into account, the behavior of the wind. There's something else we don't quite know. There's somehow the wind starts. Again, we don't exactly know where it starts. This is very, very delicate physics and limited by observing, but many people are very interested in this. What is the base temperature where the wind is really launched? Also, what is the density there? Base temperature and base density. The temperature creates temperature gradients, of course. That drives the wind in that simplified model. So you expect higher flow velocities for a higher base temperature. Density, of course, is the material. If that density is higher at the base, you get more mass loss. Now we know for the Sun, we don't know for other stars. Nobody has seen a wind in another cool star. They're very difficult to measure. It's not clear how to measure them. Well, ideas are there, but the sensitivity isn't there. Now you can fit, again, at least we have observations from the Sun. This is the profile up to 1 astronomical unit, density, speed, temperature. These are observations. This is a fit using such polytropic equations of state. And what you get is some sort of baseline level you take for your calculations. The wind starts at a temperature of about, well, 2 to 4 million degrees. That's like the coronal temperature approximately. And these are densities values that you plug in, and you can describe phenomenologically how the wind actually expands. Good, this is preparation. Now we need to develop this program, this model going through this program here. What we need to know to understand spin down and winds and all that, and actually also radiation in the end, we need the rotation rates as a function of h. We actually need to look at what the stars tell us. The Sun itself doesn't tell us much. It has 1 point in the equation. The spin down rate, once we have this, spin down rate is the omega over dt. That's torque over moment of inertia. That's just basic physics. If the moment of inertia of a star we can calculate from internal structure models. The torque, that's a difficult one. If you have magnetic fields and the wind flowing away from a star, the torque must be a function of the magnetic field itself. If you don't have any, you don't have torques. The mass loss rate, if you don't have mass loss, there's no torque. And omega. And this has been simulated in very simplified but sophisticated models in the computer. And I show you what these people, Matt et al. And also others, found from such simulations. The magnetic field must now be quantified. I need more equations. We have the magnetic field here and here again. The magnetic field is probably a function of the rotation rate. Teresa talked about this yesterday in all detail. It's a magnetic dynamo in operation. And we can take observations to sort of find how the magnetic field scales with omega. It goes to the power of 1.3 from observations. The last one and the most tricky one is mass loss, because we cannot look at mass loss on stars. We don't see solar winds around other stars. But it's probably a function of omega again on the rotation period or rate, because it has to do with magnetic fields in a way, and maybe it's a function of the stellar mass. Let's go on, develop this. It's not so difficult here, this. I mean, there are lots of intricacies in the whole process. I don't want to mention all of them here. But this is angular momentum. J is the moment of inertia of the star times the rate of rotation. Take the time derivative, just copy it down, time derivative on each side. Solve for d omega over dt, that's this one. Just solve this equation. You get 1 over I, and this is the torque dj over dt, comes from here down into this. That is the torque acting on the star. And that spins down. So you see, spin down comes with torque. This is the change of the moment of inertia of the star. If the star is on the main sequence, once it's there, it doesn't change. So this term is 0, the first order at least. Just to wake you up in the early morning. This is what the torque formula by Matt and colleagues is. You see torque, actually, they found this in computer simulations, scales with the magnetic field, with the mass loss rate, and with the rotation rate. We just take that over. Don't look at all the other little constants and terms. Good. Now we need to check with observations. We've seen that again yesterday in Teresa's talk. These are observed rotation periods, slowly rotating, large rotation period up here. At 150 million years from stellar clusters, you also have fast rotators. At 550 million years, this becomes a function of mass. Mass, rotation period, they're all the same, sort of. So there's convergence, but there's also spin down. You see that all these fast rotators spin down, the rotation period gets longer. Now we can go to this equation that was so tough, m dot, mass loss rate. It's probably a function of the stellar size, large size, more mass loss, the stellar mass somehow maybe, and omega. But we leave it open what it is. We fit these exponents a and b to explain these observations. So these observations tell us what a and b should be. And the solution is, need to get this started. What you saw also yesterday, I'm just repeating this very quickly. This is a rotation period in time. You see they all go slower and slower and slower. First the more massive stars, then the M dwarfs as well. And that's where we are now at 4 billion years. You see the Sun at 25 to 27 days approximately. Good. Now you can derive from this model, you can derive all the properties that were computed in the program in the background. This is the stellar wind in time for the same stars. You see stellar winds come down in time. It's 100 million years, 500,000, 2,000. Winds come down, they get less and less, less and less. And here, that's where we are now. The Sun is a bit lower than this, about down here. This is a saturation line, essentially. You cannot get higher than that. That's an observational fact as well. The X-rays and the magnetic field saturate. There's no more you can do if you spin up the star even further. Now let's extract that one solar mass. Let's extract the timeline. That's what we get. This is a solar wind mass loss in time, 100 million years to the present day of the Sun. The Sun is down here. But the spread here, you cannot do without this. That's the distribution we had in all these little dots in these many observations of stars. They have different rotation periods at the same age. So the wind could also be very different at a given age. We don't know what it was for the Sun. This is just solar-like stars. They fill this area. We don't know what the wind mass loss was. So now I want to add a few things where I will link to habitability. What does this have to do with habitability? We are discussing winds and rotation periods of stars. This is an X-ray or extreme ultraviolet image of the rotating Sun. You know these things. There's magnetic fields. There's heating going on up to a few million degrees. But the effect that this light has, it gets stuck in the higher atmosphere of a planet. It heats the higher atmosphere. In fact, the high atmosphere, the thermosphere and higher in the Earth is about 800 Kelvin or 1000 Kelvin, depending on the solar activity level. It's very hot up there. If you go too far with X-rays, you evaporate the atmosphere completely. Well, completely. You can actually lose the whole atmosphere of a planet. It happens on the Earth as well. The Earth actually evaporates gases into space. It's not much. There's no problem. We'll continue with our atmosphere. But in very intense situations, you may actually do a lot of harm to a planetary atmosphere. This is also called thermal loss or evaporation or whatever. There are other processes that I'm not going to mention, like non-thermal processes that interacts between wind and the upper atmosphere. There are lots of things going on. Now let's go back. Let's go back to the formation time of a planet. We learned yesterday, for example, in Inga's talk, we have protoplanetary disks. This is just a sketch. And that's where planets form. Now, planets initially are not planets with a beautiful atmosphere or anything. They form. Here's Earth. Well, this is very schematic, of course. It grows. It doesn't have water at this time. But what it also does, the disk consists of gas and dust. Now, as this planet grows, and we heard some of this in Nader's talk yesterday, it begins to attract an envelope of hydrogen and helium gas from the disk. This is not an atmosphere, this is an envelope. And that can be a lot, and I'll show you how much it can be. These are calculations here. It's a bit difficult to read. This is log T. So this is 1 million years, 10 million years, 100 million years. That's the disk phase. We have disks up to about 10 million years. And you see the envelope mass accretes and it grows and grows. The envelope gets heavier and heavier depending on what the core mass is. This is fixed now in this simple calculation. If we are in the disk with a half Earth mass core, we have this growth curve, and that's as much mass you get into envelope. And if you get more massive cores, you actually form mini Neptunes. You get so much hydrogen comes down. Now the problem is, this is not a habitable planet. Well, anyway, the problem comes here. These are calculations, just show this very briefly. Eventually, the star, this is a disk, cross-cut from the side. These are hydro simulations. In fact, the star does the same to the disk as it does to the atmosphere of a planet. It evaporates it because it heats the surface. We heard about this yesterday. There's a heat flow, a mass flow going away from the disk. Now, once this happens, you have a hole here around the star. Now there's direct irradiation from the star to the planet, and now this process begins, so as I mentioned, the evaporation process of planetary atmospheres. But before this happens, just taking away the disk releases pressure on the planet's envelope that it collected. And so the envelope expands and gets partially lost. And these are the curves of loss just by pressure release. Again, this is a small core, 0.1 Earth mass, 0.2, 0.5. These low mass cores immediately lose their envelope. That's the problem of small planets. They don't keep them. But maybe it's not a problem actually. Just let me continue a little bit. The heavier planets, if they are already in the disk at a mass of 0.5 to 1 Earth masses, they have a problem. They keep to their envelopes because of gravity. And these are mini Neptunes and not planets. This is not a habitable planet. So we are stuck here. If the planets form early, if they get to have to 1 Earth masses in the disk already, they have to attract so much envelope gas, hydrogen, helium, and trace gases, that they become like Neptunes, mini Neptunes maybe. What do we do? And now comes the star. Star helps us getting this solved. These are simulations, calculations, hydrodynamical simulations and calculations, assuming that we have such an envelope. It's just at 100% here. We just normalize this. And now we irradiate this atmosphere for a long time by stellar X-rays. 10, 100, and 1,000 million years. Now we calculate how the envelope evaporates into space. Now, why should evaporate? If you take a rapidly rotating star, and we heard about this yesterday, it produces more X-rays. It produces more extreme ultraviolet. It heats the envelope and it lets it expand into space, as I said on a few slides ago. If a star doesn't rotate rapidly, it doesn't produce much X-rays. The sun is not so active in X-rays. Could be 1,000 times more, and it maybe was in the early time. So it all depends on rotation. Now you begin to see the connection. We need to know what the rotation period of the star is to say how active it is, how much X-ray emission it has, to see whether these envelopes are going away into space. And these are the calculations. If you start with a rapidly rotating sun, like one that has 1 day of rotation period at the beginning, it spins down, we know that, but it's fast at the beginning. Then the atmospheric gas, or the envelope gas, actually goes away very, very rapidly. It drops down because it's lost into space, and after 100 million years it's gone. That's good. That's good for habitability. We want a real atmosphere. If you have an inactive star, a slowly rotating star that starts out with 10 or 15 days of rotation period, you don't get rid of this envelope. You keep it. You get mini Neptunes. That's bad. So you begin to see the trick. We need to understand the star. Now this also depends on mass of the planet because of gravity. A small planet doesn't keep to its envelope as much as a massive core does. And I'll show you here just in a sketch calculations. This is up to 100 million years, a given X-ray emission level. A massive core doesn't, as I already said, doesn't get rid of the envelope. A low mass core does it easily. Good. So we begin to see mass of the planet matters, but rotation of the star matters as well. Do these mini Neptunes exist? Just an observational interruption here. This is a diagram of observed stars for which we know mass, radii, and densities therefore. This is the mean density of a planet in grams per cubic centimeter. It's about 5 and something for the Earth. This is the planetary mass in Earth masses, 5, 10, 15, and so on. You see those planets down here, they have an average density, material density of about 1 gram per cubic centimeter. That's not rock. Rock is heavier. So there's a lot of gas in these planets. And they're a bit heavy. They're 5 Earth masses, 10 Earth masses. That's exactly those that kept to an envelope. They have a hydrogen envelope. These planets are not habitable. These envelopes are very hot, by the way, as well. High pressure. Now, this is the hydrogen envelope. We want to get rid of this, so we shouldn't have too heavy cores in the disk. Can build them later, maybe. And we need to be careful with the X-ray radiation from the star, and therefore its rotation period. Now, eventually, we will have a real atmosphere around the planet from outgassing, volcanism, or whatever, or gases that are brought by meteorites, as we heard also yesterday. Eventually, we form a real atmosphere, maybe out of carbon dioxide, nitrogen, and whatever else. How do we behave here? You can do such simulations as well for such atmospheres, but they're tricky now because there's a multitude of things: pressure, composition of atmosphere, and so on. I could show you millions of calculations. I'll just show you one. This is Mars, a simulation for Mars consisting of still hydrogen, but it has oxygen now and carbon, so it begins to have a real atmosphere. This is at 0 million years, it's just at the beginning when it formed, up to about 12 million years. And interestingly, if you radiate Mars with an intense sun, as it probably was in its early years, more X-rays. The atmosphere, even if you have 108 bars of water and 22 bars of CO2, that may have been at the very beginning, we don't know. These curves all drop, and after a few million years, depending on the model assumptions, after a few million years, maybe 10 million years, the atmosphere is gone. Now, that's not what we want. This shouldn't happen now. We want to get rid of the envelopes, we don't want to get rid of the real atmospheres. What's the problem? Well, the problem that Mars has is gravity. It's small. It doesn't keep to its atmosphere. And the X-ray radiation from the sun just wipes it away. It erodes it. So Mars is very likely cannot keep a big water reservoir, at least initially, because it all goes away. There's probably no plate tectonics because of that. We heard that yesterday in Doris Breuer's talk. It's the low gravity and the young sun's XUV radiation. Of course, if there's delivery of an atmosphere of volatiles later on by meteorites and comets and whatever, yes, you can rebuild an atmosphere, but here it's very difficult to keep it. So we have issues here. We have a time scale issue or a mass issue as well. If the planet is too small, it loses any atmosphere, and we see that in present-day Mars. It's a very thin atmosphere that it keeps. So again, this makes it difficult for a planet to become or to stay habitable. Good. So if I may summarize this, and there's a lot more one could say with all details and different atmospheres, but roughly speaking, too low mass is tough to keep an atmosphere. Certainly, it's good to lose the initial hydrogen envelope. Yes, you lose that, but you may also lose any secondary atmosphere. Too low mass is not good. Venus had another problem, of course. The mass is okay, it's like Earth, but it was too close to the sun. It was not in the habitable zone. It got hot. It lost its water by greenhouse. If you go too heavy, super Earth, if they form too rapidly, sort of in the disk already, you go to 1 Earth mass or whatever, you don't get rid of or you probably don't get rid of the envelope, of the hydrogen envelope, and you form mini Neptunes. So actually, how do we do this right? We want this planet. This one got it just right, and if you do calculations, at least now for the hydrogen gas, we found that the mass that makes the planet habitable, if it forms early, I have to say that all the time, if it forms relatively early, and there are indications that this may work, Your mass is whether 1 plus or minus 0.5 Earth masses, or you have problems. That means the radius of a typical planet that becomes habitable or can become habitable should be about 0.8 to 1.15 Earth radii. And you see how the problem gets constrained that way. You have to get it right. You have to get the planet right. Otherwise, it will never be habitable. If you are in a habitable zone or not, that doesn't matter for this consideration. You have to get all these parameters right. And to conclude, my time is actually over, I believe. In a summary, to get you the context why I discussed rotation and now end up with atmospheres and habitability, we want this. We form in a disk, we form an envelope around the growing core. We want to remove this, we want to get to a real planet with a secondary atmosphere, but we don't want to lose the secondary atmosphere. You want to go back to Mars. Mars is just okay, maybe, but it's a very thin atmosphere. To get that right, to understand this, we need to know the coevolution of the activity output from the sun or from the star. This evolves as well in parallel. And to get that, I'm going to go back to Theresa's talk, of course, we need to know magnetic fields. And to understand the magnetic field evolution, we need stellar rotation. And to be precise, we need to know the rotation rate of the star as it gets born. Or let's say after it loses its disk. And at that point, if the rotation rate is wrong, you may get all of this wrong. So you see the connection, stellar rotation, initial conditions matter a lot for what we have. It's not enough to go out there, observe stars and say, oh wow, it's in the habitable zone. That must be a candidate for water. It's not enough. All the history of a star, all its evolution, the initial conditions, they all matter. And only then can we, if other factors are not making any problems, only then can we actually get a habitable environment like on our Earth. Good, I think my time is over, and that's it. Thank you.